4, 5. Okay.
All right, so welcome everyone to the GADEPS seminar. So today we are happy to have Luo, who will speak about periods and completions of fundamental groups.
Oh, thanks. Sorry, I just moved into this new place. I'm not sure about the internet connection, so please stop me if I'm stuck or whatever. So I will start with elementary definition of periods. These are just numbers as integrals of rational differential forms over domains defined by polynomials inequalities with rational coefficients. So this is a definition by Kontsevich and Xavier. And all the algebraic numbers are periods. And I gave you two examples which are transcendental numbers. One is log 2, the other is zeta 2, which is a special value of the famous Riemann zeta function. And it can be written as an integral in this form. And more generally, we have these multiple zeta values. They are defined by convergent series, which consist of reciprocals of powers of integers. And they are periods given by same kind of form of these integrals, which we call iterated integrals. So what are iterated integrals? These are, if you are given a smooth manifold and a path parameterized, and if you are given a string of one forms, omega 1 through omega r, and if you pull back omega j, you get fjt dt, and then you string them together and put it into some kind of time-ordered fashion, and then you do this time-ordered integral, and this is called iterated integral. So for example, what we've defined, the multiple zeta values can be written as iterated integrals. So you start on the space C minus 0, 1, or P1 minus 3 points. You have two one forms. Omega 0 is dz over z, and omega 1 is dz over 1 minus z. And you have a path from 0 to 1. Then for each index ni, you get a block where it's just a string of omegas. It starts with omega 1 and then a bunch of omega 0s. Then you string them together and you find this iterated integrals. So I was lying a little bit because this is not really a line in the space. It's from 2 points that we are omitting. But this is a slightly technical point I want to skip. What you can do precisely is do some kind of what we call tangential base point. But I think I won't talk about this in this talk. But as long as you have started with omega 1, and if you end with an omega 0, then this is a convergent series, and you can compute it. It's a finite number. So another definition for iterated integrals is by considering a system of differential equations where you have these auxiliary functions y0 through yr minus 1, where you're stipulating that y0 of t is always 1, a constant function, and you do this integration process iteratively, r times. And then the end result, yr, would agree with our previous definition. But I didn't really put the paths of the integration, but for each of these r integration, it's the same path. You want to do this r times, and then you would get the same result as this iterated integral at the end. So while we are doing this, so we find that this iterated integrals is naturally comes equipped with this sort of unipotency or nilpotency, because this differential equation, when you write it in this matrix form, you get this matrix which is powers to 0 when you do its maybe r plus 1's power. And that's like a defining property for the iterated integrals. So why we care about this? Let me just put these together. So we can view these periods in another way, which is probably a famous theorem by Grothendieck in the 1960s, where if you start with some smooth variety over Q, and you compute its algebraic de Rham cohomology, it's a Q vector space. And you can also compute its Betti cohomology. It's the singular cohomology of its associated complex analytic variety. And what you do is, if you have a closed J form on X, and if you have a if you have a J topological cycle, you can integrate it, and then you would get these periods in this comparison isomorphism. It's basically comparing the different Q structures on both sides. Sorry. And similarly, in the 70s, Chen has this pi1 de Rham theorem, saying that if you have a complex manifold and a base point P, you find its fundamental group, and there would be this isomorphism where on the left-hand side it's closed iterated integrals on M. So here closed means it's homotopy invariant relative to endpoints or base point. On the right-hand side, you do this kind of some algebraic operation. Basically, it's, as I will define later, it's the coordinate ring of the unipotent completion of the fundamental group. So what we do is sort of, you start with the fundamental group, you have this group algebra, and there's a natural homomorphism from the group algebra to C, where you send every element of pi1 to 1, And this map has a kernel, which is called the augmentation ideal, which I denote by J. And its power defines some sort of topology on this. And what you do here is compute its continuous dual of the group algebra. Anyway, in this way, we sort of have these periods of fundamental groups. And there's actually a way to combine the pi1 de Rham theorem and the algebraic de Rham theorem. But this is where probably the only place I've made a little bit contribution in this talk, where you can sort of do this abstractly in theory, but to work with periods, you need to do this explicitly. And I've done this for the elliptic curves and the modular space of elliptic curves. Anyway, then you can ask, why do we care about periods of fundamental groups? So that's a long story. I want to do some background on mixed-state motifs. So eventually we will see that these fundamental groups or periods or motifs associated to fundamental groups, they can generate a lot of extensions of motifs. And that's why it's probably a very interesting object to study if you want to study the category of motifs. And the mixed-state motifs are one of the basic, most fundamental set of motifs, I guess. So they are successive extensions of Tate motifs. They have Betti, de Rham, L-adic realization. The L-adic realization is a Galway module, GQ module, which I won't talk about in this talk. And the comparison between the Betti and the de Rham realization provides periods, as we see before. And together they would define a Hodge realization, which is a Q-mixed Hodge structure. So a typical example is like this. So it's a relative homology of GM with 1 and X, relative to 1 and X. And it's a mixed motif where it has two pure parts. One is Q0, the other is Q1, which has weight -2. Anyway, they sort of combine together in a specific way and give you this extension of Q by Q1. So why is mixed-state motifs important? I guess this is the only place where we know how to construct genuine motifs. And actually we have a Toknocking category of mixed-state motifs. So if you are, so this is for people who are not familiar with Toknocking categories. Basically, you can think of this as a category which is having the property of what you would expect to have if you have a category of finite dimensional representations of a group. So its objects are like vectors, F vector spaces, and it's an abelian category, so it has kernel, co-kernel, and it has a tensor product and duals, and there are some compatibilities between these things. And it's a neutral Toknocking category if you are equipped, if this category is equipped with a fiber functor, which is a faithful functor to the category of vector space over F. So if you have a neutral Toknocking category, the good thing is you get a group for free that acts on them. So it's equivalent to the category of representation of an affine group over F. And this group is what we call the Toknocking fundamental group. And it depends on the trace of fiber functor. And we denote it by this. An examples, easy example is you do semi-simple Tate motifs, so direct sums of these QNs. And it's Toknocking, basically because this is a category of these objects are graded by weights. So basically it is just like a category of representation of the multiplicative group. The other example is the category of Q-mixed Hodge structures. And then there's this big theorem, which is what I mentioned before. The result is that there is a Q-linear Toknocking category of mixed Tate motifs over OKS, so some ring of integers ramified outside some finite set of primes, whose so maybe I will say why I put these names here. So I believe Voevodsky constructed a triangulated version of this category, and then based on suggestion of Mark Levine, the Ling and the Gontroff was able to construct or maybe extract a T structure out of this, and therefore constructing this category of mixed Tate motifs. And they are with the correct X groups, which are supposed to match up with these algebraic K series. And I put Borel's name because he computed these K groups. And the reason that this doesn't work, this whole approach doesn't work in general, is that this vanishing is not none. This is called the Beilinson-Soulé vanishings. This is not none for general cases, but in the mixed Tate motif case, this is none. So now we have this Toknocking category. You have a group, which is the Toknocking category, Toknocking fundamental group. I only do this for mixed Tate motifs over Z. So it has a reductive part, it's just GM, multiplicative group, a semi-direct product with a pro-unipotent group, K, whose Lie algebra is the free Lie algebra generated by these symbols. So as we know, the reductive part corresponds to the semi-simple part of the motif. And these pro-unipotent part, or unipotent radical part, they correspond to the extensions. For example, sigma 3 would correspond to zeta 3, which should be interpreted as a period of the extension of Q by Q3, and which is related to the K5 of the integers. So this fact is what prompted the Lin to write this his seminal paper in 1989. Long before 2005, where he basically computed one of the periods of the fundamental group of P1 minus 3 points, and was surprised to find this theta 3 showed up. And I forgot maybe he asked someone, and then someone told him this is related to the fact that zeta 3 is related to some K5 of the integers or something. Anyway, that's why we care about these unipotent fundamental groups now. It was also confirmed in like 2012 by Brown's result that this action of the Toknocking fundamental group of the mixed-state motifs on the coordinate ring of the unipotent fundamental group is faithful. And this gives you, this tells you that periods of every object of the category of mixed-state motifs are just linear combinations of multiple zeta values. And more importantly, this tells you that each of these extensions that corresponds to these odd zeta values basically would show up in the coordinate ring. And then, so there's sort of another way to construct this category of mixed-state motifs. It's by saying that this category is generated by this coordinate ring of the unipotent fundamental group as a Toknockian subcategory of maybe mixed Hodge structures. So this seems like a very promising workaround if you want to construct categories of motifs in other cases. This is what we will do later. But the price you pay that is maybe you have to work with mixed Hodge structures, and that's not really motifs. Oh, okay. Are there questions? Because anyway, then I want to talk about how one can do these completions, as we see that probably is not well known. So, so in this talk, I will basically only talk about 3 examples for fundamental groups of P1 minus 3 points, or an elliptic curve minus identity. These fundamental groups would be 3 groups with 2 generators. And then the fundamental group of the moduli space of elliptic curves is SL2Z. So when you start with discrete group, like these fundamental groups, and when you have a reductive group and also a Zariski dense homomorphism from the discrete group to the reductive group. What you can construct out of these inputs is this what we call the relative completion of gamma with respect to this homomorphism. It's a pro-algebraic group, which is an extension of R, the reductive group, by a pro-unipotent group. When R is the trivial group, like in this case, then the homomorphism would obviously be trivial. Then what you get is that the end result would be called the unipotent completion of the discrete group, and I will denote it by the subscript, a superscript UN. So here's the result. This is F2 unipotent completion, and here this is the notation I will use for the relative completion of SL2Z with respect to this inclusion. So I only told you the end result. Here's how you actually define the relative completion. So again, this is the Toknocking construction. You can consider the category of remember you have these inputs. You have a discrete group, a reductive group, and a homomorphism between these. So if you consider the category of finite dimensional gamma representations, V, which admits a filtration, a finite filtration, whose graded quotients can be acted on by R, which is through this homomorphism that you started with. Then this category is a Toknocking category. It also has a fiber functor, which is the forgetful functor. Then the relative completion is just the Toknocking fundamental group of this category. To study this relative completion, as we said, we have this short exact sequence by Levy. It's isomorphic. This relative completion is isomorphic to R semi-direct product. It's unipotent radical U. And because U is pro-unipotent, it's equivalent to study its Lie algebra. Assume then that every irreducible representation of R is absolutely reducible. That is, when you extend the scalar from Q to Q bar the algebraic closure, then the irreducible representation will still be irreducible. Then that's called absolutely irreducible. So in our cases, the three cases in this talk, these are all satisfied because it's just either it's trivial or it's just SL2. Then we have these, you can compute H upper 1 of U and H upper 2 U. So here R dual denotes the set of isomorphism classes of irreducible representations of R. And for each isomorphism class alpha, you pick a representative V alpha. And you do this with its V alpha dual, and you tensor this, and you get this direct sum. And then the Lie algebra has this structure, which is, it is generated by H lower 1 U, the free Lie algebra, and mod out by relations by H lower 2 U. So in particular, for relative completion of SL2Z, we have the H2 part. H2 for SL2Z is, because SL2Z is virtually free, this is 0, so its H2 would be 0. So there's no relation. So that the Lie algebra in this case would be a free Lie algebra generated by H1 of UREL. And if you put in the formulas in the last page, you would get this, where H is the standard representation of SL2, and S2n denotes its 2n's symmetric power. And this line, I just write it as a Hodge structure for those who know, which basically by Eichler Shimura, this space can be divided into two parts. One is split into the Eisenstein part and the cuspidal part, where the cuspidal part well, it's easier to work with vector spaces over 2 bar than the VFs would have rank 2, twisted by 2n plus 1. So once you've written H1 into this form, and because UREL is just the free Lie algebra generated by these, we know that the weight graded quotients of UREL would be of the form VD, where it's just some symmetric powers of these VFs tensored together and then twisted by some number, where these FIs are distinct Hecker-Eigen cusp forms. And this would be a typical example of mixed modular motifs. And so motivated by previous result of mixed state motifs, Raum proposed the following definition, which is, we can sort of define the category of mixed modular motifs over Z to be the full Toknockian subcategory of mixed Hodge structures generated by the coordinate ring of relative completion of SL2Z. And their periods would be called multiple modular values, and they are given by iterated integrals of modular forms. So here's the real game. I want to, we play like, so this is, so what we really do is that we don't have a, because we don't have a genuine category of mixed motifs. So we work in this category of Betti and Raum realization, equipped with some mixed Hodge structure data. So the objects are these triples where V Betty, V Durham are finite dimensional Q vector spaces. And there's this sort of comparison sort of isomorphism when you tensor it with C, and then there are some other data related to weight and Hodge filtrations, which I omit. So the important thing is that this is a Toknocking category. Then it's equipped with this Toknocking fundamental group with respect to the Durham fiber functor. And we would call this group the motivic Galois group. It's like a group acting on these kind of motifs or periods, if you like. So this is similar to the case of classical Galois theory. If you think back, when you define a classical Galois theory for algebraic numbers, you find the symmetries from the defining equations of these algebraic numbers. Here, we sort of going through all these machinery, trying to, we get a group or a symmetry that's acting on probably the defining integral of the periods. And then the idea is to study this action on these sort of special objects where, as we mentioned before, the coordinate ring of the unipotent fundamental group of P1 minus 3 points, and the coordinate ring of the relative completion of SL2Z. So as we study them, let me just put down the notation. We denote by this, the Lie algebra of the unipotent radical of the motivic Galois group. This is called the motivic Lie algebra. In this Lie algebra, there should be these zeta elements we mentioned before that corresponds to all the zeta values. So they correspond to these extensions. And there should also be modular elements corresponds to these extensions, where for every Hacker eigen cusform and a suitable integer d. There are actually a pair of them. More generally, you can predict the number of these elements because we have this Bayes conjecture predicting the dimension of the extension of this kind, and it would correspond to the same amount of. It should correspond to the same amount of elements in this motivic Lie algebra. So the real thing that we play is that if you kind of trying to construct these extensions is usually very hard, but what we are putting ourselves in is that we have this motivic Galois group that can move things around, so that maybe we can in some way move these things into a place where we can compute, and then we can predict what kind of extensions that can show up, or maybe when we sort of also well, if there's enough evidence that this works, maybe we can do this for every extension. But right now it's just not very promising because it's very hard to compute. Anyway, I'm already on the final page. So I would summarize what we have. So what we have is that we have discussed actually only two cases here, but the other case, the elliptic curve case, would be similar. So we start. So this column would be what we know as the column for mixed-state motifs. So let me just go through this column first and do the next two columns. So we can start with, so to construct mixed-state motifs, we can start with this P1 minus 3 points. And then, as I wrote here, you can think of this as a moduli space of genus 0 curve with 4 marked points, because you can put 3 points into 0, 1, and infinity. And then the last point would be in the complementary of P1. So this would
I think his internet is gone. So let's a little bit wait. Okay, I think Luo is disconnected. Maybe just I stop recording or. Yeah, exactly. This is. So just a moment. Just wait a minute. I am beginning recording. It doesn't come, but.
It is recording. For me, it is recording.
Well, for me. Okay, go ahead. It is for me. It is still turning. Okay, go ahead.
Is it okay?
Yeah, you can continue.
Okay, I'll just probably start with this. This is actually my final page anyway. So this, I think, so I talked about the completion of unipotent completion of fundamental group of P1 minus 3 points. And then you do this coordinate ring, which by Brown's theorem generates the category of mixed-state motifs as a category, meaning that you do subs and quotients and tensor products, duals, and you basically generate the whole category. And then you have this, in this case, we know the structure of the motivic Galois group. So I was cheating a little bit because I only define what you would call the absolute Galois group. What the actual Galois group in this case is like a quotient of it. But I talked about the structure of this Toknocking fundamental group of the of the category of mixed state motifs, whose Lie algebra is just a free Lie algebra generated by these zeta elements that corresponds to the odd zeta values. And here are what their periods are. In general, it's just iterated integrals of the one forms I talked about, omega 0 and omega 1. So basically, namely the multiple zeta values. And the pure periods are just 2 pi I, the powers of 2 pi I. And some others are just these odd zeta values that corresponds to, you can think of them as periods of the extension in this case. And then in the case of moduli space of elliptic curve, the fundamental group would be SL2Z, and you do this relative completion. The reason is that the unipotent completion of SL2Z would be trivial, as it has like a torsion H1, I believe. And I'll skip the base point. The base point we usually pick is the unit tangent vector at infinity, or the unit tangent vector at the origin of the Q disk. But then what we want to say is we have this relative completion and we do its coordinate ring. We hope that it generates the category of mixed modular motifs. And there are, in this case, there are also these zeta elements and modular elements. And I believe Francis already found all these elements in this case and showed that these indeed generate a Lie algebra, and they are like free, meaning that these extensions, the extensions corresponds to all zeta values, and these Hacker eigenforms, these simple extensions exist in this coordinate ring. And the next set of elements we would like to find would be these so-called Rankin-Selberg elements. To find these, so just like in the mixed state case, the reason that we were able to find these extensions and compute all these is that we can write down the periods quite explicitly, and we can compute the motivic action quite explicitly by a work of Gontrov and Ihara, and this is not available in the mixed modular case. But there are still hope, because we can sort of compute these iterated integrals of modular forms. Maybe one just has to be lucky to put these into the right, correct situation so that we can confirm these extensions. And in this case, the pure periods are the critical values of the L function associated to Hacker eigenconforms.
Maybe the modular forms appearing here, just the Hecke forms of weight too, or you need more?
Oh, you have all the weights.
But they are Hecke forms, or?
Hacker eigenforms, yes.
Hecke, because you are using then, okay.
Yes, because I'm using, I always use maybe F and G are all Hacker eigenforms. And then you need to put suitable the it's in the critical strip of the L function associated to F. And for the extension part, it's again all zeta values and non-critical values of L functions. And I don't think I need to go over this elliptic case very much, but the basic idea is the same. You start with the punctured elliptic curve, you have the fundamental group, do the unipotent completion with a suitable tangential base point, and you do the coordinate ring. It's supposed to, but we don't know yet, to generate category of mixed elliptic motifs. And there should be these elements where H here is just H of H1 of E. And you should have these symmetric powers. And the periods are iterated integrals of the abelian differential and the differential of the second kind, and so on. And the pure periods would be these elliptic integrals, and some other the extension data would come as like L values of L functions associated to elliptic curve. I think, yeah, I have time for questions.
Okay, you are
Thank
finished
you.
now.
Yes, I'm finished. Yeah.
All right, so questions?
Maybe this, I have a general question. From these three examples that you took, only the last one has a moduli. This means that it is you can deform it because P1 minus 3 points on the other one. I mean, well, the second one I don't know, but anyway. I mean, if you have this, let's say family of elliptic curves. And at the end, all these numbers, iterated integrals, they depend on parameter. They're just not numbers. They become functions on the moduli of, for example, in the third column, a moduli of E. This kind of things is useful for this kind of topic? For example, to start making derivation of all these iterated integrals and so on. Something that I searched a little bit to see if there is a literature is actually when iterated integral depends on parameters, and then you want to make derivation, something like Gauss-Manning connection for iterated integrals.
Yes, there are actually. I didn't talk about this. Is work of Dick Hayne. He has this what he would call universal mixed elliptic motifs. Basically, it's like a family of these over M11. Mm-hmm. And when you specialize to the nodal cubic, it's actually this one, the one probably for this. Well, you can specialize on every fiber, like you get a punctured elliptic curve, and it would involve these variations of mixed Hodge structures. But he actually trying to, I believe, it's his work with Matsumoto, where he has I'm not sure whether he computes like iterated integrals on these things, because he's not really concerned about this. But maybe, but there are people working on, like, say, elliptic multiple zeta values. Like, I don't know if Niels is here or some other people are working on these things. Which would involve to like doing iterated integrals as like writing it as maybe a function on the moduli in terms of, or maybe the upper half plane.
So can I say something?
Oh, you are here.
Okay.
Yes, great. Okay.
I am here. Yes, sorry, I switched off my camera. So does this work now? Hi. So just to go back to Hossein's question, so about the analog of the Gauss-Manin connection. So that's something that is, well, I don't know how explicit that actually is in the work of Hein and Matsumoto. I mean, Thiago Ma mentioned that he considers families, but there's not really a Gauss-Manin connection in this work there as far as I know. But in joint work with Thiago Fonseca, we actually constructed one on iterated integrals. But this is still work in progress. So,
I know for families of curves, just not this example, just I'm not in the context of Motif. And in the graded pieces of this fundamental group, when you make this filtration on the fundamental group, I wrote few stuff in this direction, but it is mainly for applications in holomorphic foliations. But I was wondering what would be the application of this in the Motif stuff. Anyway, let me just stop recording, and then we go with the informal discussion.